Hi folks, welcome back. So in my last video I had a few comments that asked me if I could do some like example problems with like the circuit theorems, because I feel like there are quite a few of you who would find that helpful. I was trying to avoid doing stuff like that because I don't want people to see all of the calculations and maths and switch off. So I thought it might be good to just do a short video with just a couple of example problems in it, and then that way people who don't want to do that kind of stuff can just not watch this video, and those of you who find that seeing me work through a couple of circuit kind of puzzles, that might help cement the kind of basic ideas in your head. So I'm going to do a couple of simple examples, just a couple of resistor circuits, and so hopefully this helps some of you out. So see you in a bit. Okay, so we're going to do a bit of a, so we went over a pure series circuit in the actual Circuits 101 video. So I won't go over another one because they're all basically the same as that. You find the total current, and then with the total current you can find the voltage drop across each resistor. It's very straightforward. What I'm going to do here is I'm going to go over a slightly more complicated kind of series and parallel circuit, and then I'll go on and I'll do a much more complicated one with some more techniques that we did in the Circuits 101 video, just to show you how you can take the ideas that I've already taught you and expand on them. There are more complex circuit theorems that are really just the basic circuit theorems given a new name. So we've got this 4 resistor network, we've got 200 volts across it like this. So we want to find, first we want to find this current. We're going to call this I0, that's the current coming out of the power supply. And then we want to find the current and the voltage across each single resistor. So, we'll name each resistor. Okay, so, where do we start with this? Well, we start the same way that we started before, which is that we want to find, the first thing we need to find is the total current. And if we want to find the total current, the way we do that is we need to find the total resistance. And now, the way we find the total resistance, well, we've got this, and then we go into this parallel thing here, and then this comes out, and there's another thing in series. So we kind of need to think of this as we've got this in series with these two in parallel, which is also in series with this. So the first thing we want to do is I'm going to redraw this as 3 series resistances. Okay, so what we're going to do is we're going to collapse these by working out the parallel resistance into one, and then that will allow us to just add all 3 resistances together. And that's what this kind of circuit analysis is really all about. It's about redrawing the circuit in a way that makes it really easy for you to solve it. So I'll call this one R5 because this is now a new resistance, or we could call it R2 plus 3 or something. I'm just going to call it R5. And maybe let's make a note over here, just so we can keep track of everything. Okay, so, and then we got R4 in series here. So to work out this current, and this is still 200 volts across here, all we need is to work out what is the value of R5, and hopefully you've watched my Circuits 101. If you haven't, go and watch that if you're not sure what I'm talking about at any point. The value of R5 is going to be the parallel combination of R2 and R3. So instead of writing like this, you'll sometimes see when there are 2 resistors in parallel written like this, and that means R2 in parallel with R3. Let's work that out. And the parallel combination of R2 and R3 equals, and we use that product over sum rule that I spoke about in my last video, which is when you've got 2 resistances and only 2 resistances, no more, no less. If you have more, then you have to add 1 over R1 plus 1 over R2 plus 1 over R3, and that gives you 1 over the total resistance. So you then, if you did this in a calculator, you do this, and then you get your answer, and you put it to the power of -1, which is just a button on your calculator that you can press. But usually we try and get it so that there's 2 in parallel. We've got R2 plus R3, so that's just going to be the product over the sum. So 6 times 2 over 6 plus 2, 6 times 2 is 12, 6 plus 2 is 8. Divide the top and the bottom by 4, so 8 divided by 4 is 2. 12 divided by 4 is 3. So we've got 3 over 2 ohms. Right, so 1.5 ohms, we'll call it. So, we've now got the series combination of R1, which is 2.5, and that will be our total resistance. So, if we want to find this current, what we want to do is we just add these three together. So we've got 2.5 plus 1.5, which is 4, plus 4, which is 8. So we've got 200 volts divided by 8. So we can now see I0 is 200 is, let's be, V over R total, which is 200 divided by, what was it, 8, which is equal to 200 divided by 8, 25. Okay, so now we've got this I0. We can start piecing together the rest of this little puzzle. So, like I said before, we can think of this as kind of 3 chunks of resistance. And so we know that these 3 things are in series, so we know these 3 blocks are all going to receive the same current. So now we know I0, and we know that this is in series with this, is in series with this. Well, now we know the current through R1 and R4, because it's just I0. Because this is in series with this, like the current coming in here has to be the same current coming out here, right? And the current through this wire has to be the same current that flows through this resistor, you know, because they're all in series. So, sweet, we can start filling in these. So we got IR1 equals 25, we got IR2, we don't know, IR3 we don't know, and IR4 we know is 25 amps, I should say. Don't forget your units. You're doing an exam, you lose a mark. Now we just need to work out how much current is going through here. Well, now we get a chance to apply our Kirchhoff's current law. So we know that I0 is coming in here, and so we know that IR1 plus IR3 equals I0, or I0 minus IR2 minus IR3 equals 0. This is our KCL equation, you might hear it written as. If we knew one of these, this would be super easy. We don't know either of these, so we can't solve this equation yet. But we can just use a bit of our understanding of circuits, and we know that the ratio of these two resistances is also going to be the ratio of the currents. So there's this thing called the current divider equation, which works out, so you know how there's like this duality between currents in parallel are shared, just like voltages in series are shared instead of being equal. And voltages in parallel are equal, just like currents in series are equal. There's that duality, there's that with a lot of things in electronics. So there's a current divider equation, which works the same way, the same kind of format as the voltage divider equation that I showed you before. So that basically works with, you take the resistance that the current branch that you're looking for, so let's look for IR2, and that equals the current in, so which in our case is going to be this I0, so we'll call it I0 times, and so the voltage divider equation was this, where you took the V that you wanted, so let's just call that V out, and that was V in times the resistance that you want to find on the top over the sum of the two resistances on the bottom. And now the current divider equation is kind of the opposite of that, where you take the resistance that you don't want on the top, right? And so if we're finding IR2, we want IR3, we want R3 on top, and then R2 plus R3. Right, I won't go into how you derive this. You know, if you want an equation, there you go. And I've taught you the non-mathematical way to think about it just beforehand. That will be 25 times R3 is 2 over 2 plus 6. I'll write all that. 2 plus 6 equals 25 into 2 over 8. So you're basically saying, what's the current coming in? What's the ratio of the two resistors? And is 6.25. And then if we change the numbers around, we'll have 6. This is 18.75. Okay, so we now know IR2 is 6.25 amps. IR3 is 18.75 amps. Now we're on the home stretch and we want to find the voltages across each resistor, and that is just as simple as taking your Ohm's law, V equals IR. Okay, so you write out an equation for each separate resistor, the current going through that resistor times that resistor's resistance. So we've got IR1 is 25 times 2.5 is going to give us 62.5 volts. 62.5 volts. And then we know our VR4 is going to be 4 times 25, which is 100 volts. And now VR2, we have 6 times 6.25 amps, 37.5 volts. And VR3 is 2 times 18.75, which is 37.5. Okay, great. So let's write all these down. There are a couple of moments where, like, if these two had come out as a different number, that should have raised the red flag, because these two, we know these voltages across these two resistors that are in parallel should be the same. And so now there's one final test to pass, which is we do our KVL loop equations one more time, just to check that we've got the right thing. So we've got our source here, and the voltages around each closed loop should add up to 0. So don't fall into the trap of thinking that this is a loop, or that these two in parallel are a loop. We need two separate loops, one that goes around here and one that goes around here, and they should both add up to 200. So we start 200 volts. So the way I like to do this is, so we got this drop across here, we got conventional current going this way, so we got a voltage drop like this, voltage drop like this, voltage drop like this, voltage drop like this. Okay? And then we start from the negative point and we go through the supply. So we start from here, we call this place ground, this is 0 volts. Right, let's call this ground. And then we start and we hit the minus supply, so we're going to write a minus sign. And then we've got 200 volts. Cool, 200 volts. Then we come around this way, we hit a plus sign, so we've got plus. And what's VR1? 62.5 volts. And then we go around this way, we hit another plus sign. And then what's VR3? 37.5 volts. And then keep going through, and we hit another plus sign. And what's VR4? 100 volts. And then we say that this should equal 0. Well, so we've got 100, these two equal 100, 100 plus 100 minus 200 equals 0. Woohoo! And then we do the same thing going around the second loop. Hit a minus sign, 200 volts, and then this loop is actually exactly the same. We got plus 62.5, plus 37.5, plus 100 equals 0. Check. Boom. We are done. Thank you very much. So we found the total current, we found the current through each resistor and the voltage across each resistor by using our KCL, KVL and Ohm's law. And we looked a little bit at our current divider equation as well. So that was awesome. I hope you enjoyed that. We'll do one more circuit which is a little bit more complicated, It actually uses all of the same rules. It's just might be a little bit harder for you to see how to simplify it. Is usually the place where beginners stumble the most. Okay, so this looks a lot more complicated than what we were doing, but it really isn't. I think to a kind of beginner at first glance, this circuit probably looks a lot more complicated than it is. And we're going to do one really simple thing that is going to simplify this circuit a great deal. So, we've got 24 volts coming in here. You know, now that I've shown you, why don't you try pausing the video and see if you can have a go at solving this. We've got 24 volts coming in here, and I only want the current through this resistor. So have a go at that and see how you do. Okay, I'm going to assume that you've at least had a go at that. As I told you before, the key to this, that I'm sure hopefully some of you figured out, is to redraw it in a way that makes it a bit more obvious who's in parallel with who. So we're obvious that we've got some stuff in series and some stuff in parallel. So I think kind of the danger, the trap that you might have fallen into if you struggled with this, is that you started here and you're like, right, okay, well we got this, so we go through this, so this is in series with all this stuff. So we come to here and then we got these two in parallel. And then you think, right, okay, so, and then these two in parallel, and then this one in series, so we got this in series with these two, in series with these two, in series with this guy. And that is not right. So the problem that you might have come across, or the thing that might have tripped you up, is that for something in parallel, like it's correct that when you've got a fork, you have two parallel paths, but that doesn't necessarily mean that these two resistors are in parallel. The top and the bottom of the resistor have to be connected together for something to be in parallel, as well as there being the two paths. So the better way to start is to start from this side. And so seeing that these two are in parallel with this resistor, and then so we're going to redraw the circuit first. This is the great thing about doing this on the whiteboard. Let's redraw this. We've got 2 ohms and 3 ohms. So if I redraw this now, and we wanted this current here, didn't we? But now this makes it a little bit more obvious that this current here is the same here and is the same here. So we can combine these two resistances into one resistance. So let's redraw this again. So now instead of the 2 ohm and the 3 ohm resistance, we now have one 5 ohm resistance with the current that we were looking for coming in is still the same because those two resistances are in series. So we've just made this a whole lot easier. So now we can see that these two guys are in parallel because the top and the bottom are connected. Now we can't simplify this down because the current through these two aren't necessarily the same. So we're going to keep these two in parallel. So we come through here. So now we've got the top and the bottom of these segments are in parallel. So now we've got this in series with these two branches in parallel. So I'll redraw it yet again. So now we're starting to get somewhere. Okay, so now we're at a point where we can start solving this. Now this isn't the only way you can solve this, there's plenty of other ways. This is the way that I'm going to show you how to solve this one because it uses mostly techniques, only techniques that we've looked at already. To find this current, we need to find out the split of these currents. Now, obviously, I've been kind and it's obvious that these two currents are going to be the same. But to find out what, so this current will be half of this current, but we don't know what this current is. We need this current, and this current is going to be the same as this current. So what we really need to find out is the current coming in from the power supply, and then how that current splits. And so once we found the current coming in from the power supply, we can find this split, and then once we know this split, we can take this leg and find this split. Okay, so how do we find the total resistance of this circuit? So we know two resistors in parallel that are the same value, the total resistance is going to be half of the resistance. So what we can kind of jot down in our memories is that this in series with these two I'll give these all numbers. So what we want to remember is that R4 in parallel with R5 is 2.5 ohms. And so that then means that R3 in series with R4 in parallel with R5, a bit of a mouthful, 1.5 plus 2.5, remember this was 2.5, which is 4 ohms. So we know this whole leg here is 4 ohms. So now we know that the total resistance is 1.6 ohms plus 6 ohms in parallel with this whole thing, which is 4 ohms. So I can put a kind of imaginary impedance here, which is 4 ohms, which I'm just using so I don't have to redraw the whole circuit again. So this is 4 ohms, and that represents this whole branch I'm just writing down here. So we can now calculate these two things. So we now know the total resistance is equal to simply R1 in series with R2 plus, I'll call this R6. R2 in parallel with R6, and R6 is this thing here, which is this whole branch. So you can see, if I wanted to write that whole thing out, we've said that the total resistance is this, R1, in series with R2 in parallel with R3 plus R4 in parallel with R5. Close brackets, close brackets, close brackets. Right, so you can see why I've done it in stages, because this, if I'd just written this down, that would probably be quite hard to follow, but hopefully you can see how I've gone through this. So if I had these parallel, put that in series with that, and then we put that whole branch in parallel with this, which we then put in series with that. I hope that is easy enough to follow. So let's calculate R2 in parallel with R6, just to keep in line with the methodology that I've been using. We'll call that R7. So we'll say that R7 equals R2 in parallel with R6, which is going to be, remember, the product over sum rule. So R2 times R6 over R2 plus R6, which is equal to 6 times 4 over 6 plus 4, which is equal to 24 over 10, which is equal to 2.4 ohms. Can't draw, sorry. That's an ohm symbol, I promise. Now, all we need to do, so these two are 2.4 ohms. So now the total resistance is 1.6 in series with 2.4, which is 4. So now we can work out the total current coming from the power supply is simply 24, which is our voltage in. So let's call this I0. And we'll say that I0 equals 24 divided by 4, because that was the total impedance, and that gives us 6 amps coming in. Okay, so we've got 6 amps coming from the power supply. Now we just need to figure out how much is left when we get all the way down here. Now I'm going to redraw the circuit, because we can simplify this even more now that we know this current in. So the current here is the same as the current here. So if we think of this whole circuit as a voltage divider, where we have 24 volts coming in, and we have 1.6 ohms here, and then we have this impedance represents this whole network here, which we remember came out to be 2.4 ohms. So seeing as we know the current here is the same as the current here, which is the same as the current here, which is the same as the current here, because this is all in series, we don't need this resistor. We can eliminate this resistor and calculate the voltage at this point and pretend that this resistor was never there. We know from our voltage divider equation that the voltage at this point, V out we'll call it, is equal to V in times R2 over R1 plus R2. This is R2 here, this is R1, and that's equal to 24 times 2.4 over 4, which is equal to 14.4, which is equal to 14.4 volts. So now we know that the voltage here is 14.4 volts. We know the current coming out here is 6 amps. We can now pretend we've now eliminated another resistor, which is always good, simplifying everything down. And what we've just done is called the Thevenin equivalent circuit. So we've represented the whole circuit as a voltage divider, and then we can take the voltage at this point and forget this impedance, and it simplifies the circuit. It's more useful in other scenarios, but it's something that I thought I'd bring up and show you how there are slightly more advanced circuit theorems with fancy names, but are really just all this stuff we've been doing, just kind of dressed up a little bit. And the reason why I did that is that now we know we've got 14.4 volts across both of these, because these two are in parallel. So now we know that we've got 6 amps coming in here, and we know that we've got 14.4 volts across this single resistor. So that easily allows us to calculate the current through R2, and then this cut branch of the current will just be 6 amps, which was our I0, remember? I0 coming in here. And then if we call this I1 and this I2, then we want I2 because we want to know this. So we know that if I0 minus I1 minus I2 equals 0, then if we want I2, we can take I2 over this side of the equation by adding both I2 to both sides. And then we've got I0 minus I1. We know I0, we're about to really easily calculate I1, and then we'll have I2 left over. Super. So let's do that. We know that I1 equals V, which is this voltage here, over R2 equals 14.4 divided by 6 ohms equals 2.4 amps. Therefore, this I2 going this way is 6 minus 2.4, which is 3.6 amps. Oh, we're so close now. So now we know we've got 3.6 amps flowing down here. Now we don't care about this resistor because we know if we've got 3.6 amps here, we've got 3.6 amps here. So screw you R3, we don't care about you. So now we just need to find the division of these two currents, and we don't need to do any complicated stuff because these two things are the same. So we know that the current is going to be shared equally between these two because it's the ratio of these two resistances. So we know that the current here is 1.8 amps. Woohoo! So I hope you can see that that looked very, very complicated at the beginning. We've done a lot of stuff, but most of it was just redrawing. It was just redrawing, putting stuff in parallel and applying the simple circuit theorems that we know to simplify it and keep simplifying it and simplifying it until we can solve. It's like a puzzle, really. So I hope that that helped some of you who like these numerical problems. Please let me know in the comments if you want me to do more of these types of videos, because I can and I would be happy to do so if you find this stuff is really helpful. I find this stuff really helpful. I learn this way. This really helps me out. So thank you very much for watching, and I'll see you next time. Thanks for watching. Make sure you like, share, subscribe, do all that stuff. Ring the bell. Find me on social media, on Facebook, Twitter, Instagram. Watch more of my videos. Here's some over here, and I'll see you all next time. Take care.